We're now going to move on from talking about waves on strings to looking at sound waves, so longitudinal waves passing through air. As a quick overview, we've said already these are longitudinal waves resulting in a longitudinal displacement of molecules. In this case, rather than talking about x and y, we're now talking about s as being the localized displacement in the x direction. In this case, S0 becomes the amplitude of that vibration, while x is the horizontal position of the particle. Whenever we think of sound waves, we think of density and pressure changes happening in the air as those molecules move around and propagate the wave through. The density and pressure changes are out of phase with the position. The molecules are further apart at the maximum displacement value. So when we see how the pressure varies with time, we have this pi/2 component showing that out of phase relationship. The higher the pressure, the higher the density of the material, but also at high pressure, high density, we have the minimum displacement. So whenever the pressure is at a maximum, we have that minimum displacement, and we see that in this graphic here. Fundamentally, there's a relationship between the pressure and the density of the material. So the pressure P and the density represented by the Greek letter ρ in this equation. Okay, so we always talked about energy with the transverse waves. Let's look at the energy of sound waves because things are slightly different. Unlike on a string, we need to now consider the sound moving out in 3 dimensions. Wave on a string moves in a single dimension, but sound waves move out from a point source across all 3 dimensions. So on a string, we had this average energy per unit length expression, which we looked at in the previous videos. For sound, we have a change in terms of the average energy per unit volume. So we're no longer looking at a single dimension, we're looking at all 3 in a volume. But we see there are parallels between the 2 equations. Instead of a linear mass density, we have a 3-dimensional physical density. And instead of delta x, we have a change in volume, and we have S0 representing our amplitude. So the equations are broadly similar, we've just changed them for the 3-dimensional counterparts. When we think of sound wave intensity, so the energy at distance r is spread out over this spherical surface. Now we're approximating a sphere as a 2-dimensional circle here, so hopefully you can visualize that. As the energy spreads out, as it travels a further distance delta r, it's spread out over a wider area. The key thing is that the power is spread out over an area. So we're looking at the power per unit area of the surface of the sphere. As the sphere's surface gets bigger, the energy is spread out more and more. And this is related to the surface area of a sphere. So we have our intensity is proportional to the average power per unit area on a sphere. We also have the expression for the average power, which is the average energy divided by time. We then combine these into a single expression to get the intensity of that sound wave. Okay, so we had our expression for the average energy. Remember, this was simply a 3-dimensional translation of the energy on a string. For a sphere, we can find the change in volume as that, we can visualize it as this spherical shell around the original sphere. We can derive the change in volume here, so 4 pi r delta r. So taking the surface area and multiplying it by the extra amount that the sound wave travels. So as we put this expression into the first expression for delta V, we obtain this rather messy looking thing. We can now use this expression for the change in average energy and put it into this equation that we derived before for the intensity. If we put it in here, our 4 pi r squared cancels, and we end up with this delta r delta t term, which is simply the linear velocity of the wave passing through the air. And we end up with a rather simpler looking expression for the intensity. What we can now do is we can use the expression that we had earlier for how the maximum pressure relates to the density, frequency, speed, and the amplitude of that wave. We use that and we can substitute this into our expression for the intensity to get a final expression relating the sound wave intensity to the maximum pressure and the density of the material. Okay, let's look at the intensity of a wave. So how does that pressure change with the radius? Does the pressure change proportionally to 1 over r squared? Does it change proportionally to 1 over r? Is it a constant change? Or is it proportional to r? Pause the video and we'll discuss it shortly. Okay, remember our equation that we had before related the intensity to the change in average energy divided by 4 pi r squared. This is telling us that there's an inverse square relationship in the intensity. So because there's an inverse square relationship between the intensity and the radius, we take this up to the top and we see that P0 squared over 2 rho v is equal to delta EAV over 4 pi r squared. So what this is telling us is that the square of the pressure is related to 1 over the square of the radius. So this tells us that if the intensity has an inverse square relationship, then the pressure should have a straightforward inverse relationship. So the answer we're looking for here is B. What we often want to do with sound waves is to measure the sound wave intensity. Now for us, the perception of sound is logarithmic. So what we would perceive as a doubling of volume is actually a 10 times increase in intensity, approximately. And we find that a useful scale for measuring this is a decibel scale. In this case, the intensity level beta is measured in these decibels, and this is the equation relating it there. So we have I over I0. In this case, I0 is defined as 10 to the minus 12 watts per square meter. The reason for this is that this is regarded as the limit of our threshold of hearing. This is the reference value against which we compare all sound waves. A tenfold increase in intensity should lead to us having a doubling of volume. So if we want to double the volume, what we need to do is we multiply the intensity by 10 and we see the effect on the decibel level. Multiply the intensity by 10 and we see we have the original decibel level plus 10. So for every increase of 10 decibels, we have a perceived doubling of volume, or a tenfold increase in the intensity of the sound. Let's do a quick example to examine sound intensity. How far would you need to be from traffic for it to be as quiet as a library? So if we are going to say that the hearing threshold is at 0 decibels, and we're going to say that the sound level in the library is 40 decibels, and the sound level of busy traffic is 70 decibels. Just for reference, we'll say that 120 decibels is the pain threshold. So how far would you have to be from traffic for it to be as quiet as a library? Pause the video and we'll come back to it presently. Okay, so we have our 2 decibel levels we've jotted down here. If we quickly rearrange the decibel expression, we find that the intensity is 10 to the power of beta over 10 times the reference threshold intensity. If we want to find the ratio of the intensity of the traffic versus the intensity in the library, we divide these expressions here, and we end up with 10 to the power of the difference between the 2 decibel levels by 10, which gives us a result of 1000. Remember that the intensity is proportional to 1 over the square of r. So if we want to reduce the intensity by 1000, we need to increase the distance by the square root of 1000, which is approximately 32 meters in this case. In summary, sound waves are longitudinal waves. They are longitudinal displacements of molecules in the direction of the propagation of the wave. Pressure and density are pi by 2 out of phase with displacement, and you can see this in the graphic that we've shown here. The wave intensity is fundamentally a power per unit area. Although we're thinking in 3 dimensions, remember that spherical surface is the bit that we're interested in. A spherical surface is a 2-dimensional parameter, so it is a power per unit area, which means that as the sphere increases in size, the wave intensity drops off proportional to 1 over r squared. This is an inverse square relationship. We also spoke about decibels and how we measure intensity level, and fundamentally that intensity level is a logarithm of intensity. It is our perception of sound wave intensity. And fundamentally we normalize this to 10 to the minus 12 watts per square meter, which is generally agreed as being the threshold level for us to be able to hear sound. In the next video, we'll talk about sound waves in reference to the Doppler effect.